Good morning, everyone. I first would like to thank the organizer of the workshop for inviting me today. So what I'm going to talk about today is an analysis of sparse coding, more specifically analysis of its local minima. So that's going to be a little bit of theory, so I hope it's going to not be too much for such a early schedule. I hope it's going to be okay. So the topic of sparse coding has been the focus of a great deal of research over the last decade or so. And the main idea behind sparse coding is to try to model signals as a combination of a few learned representations. And so this idea has been applied to a number of different settings, for instance, in neuroscience, image processing, computer vision, audio processing, and so on. And so people have came up with different approaches to perform sparse coding. Some of them use convex tools, submodular analysis, Bayesian methods. And today we lay the emphasis and focus on the non-convex matrix factorization formulation, which actually I deem to be one of the most widely used, most common approach for sparse coding. So in this setting, we basically consider a set of n signals that are the column of this matrix capital X, and each of these signals is represented by n features. For instance, an image described by n pixels. And we also consider a dictionary composed of p atoms, which are the column of this matrix capital B here. We consider also a decomposition matrix that contains the sparse decomposition for each of the signals, and those are contained at the column of this matrix capital A. And basically the idea is to try to represent each signal as a sparse linear combination of dictionary elements. So this can be written in matrix form as this product here. X should be approximately equal to D times A. Alright. So one way to obtain the decomposition matrix A and the dictionary D is to try to solve this formulation here, where we simultaneously try to optimize over the matrix A and the dictionary D. So we not only want to well explain each signal, but we also add this L1 norm here to make sure that we only use a few dictionary elements per signal. So here I will be interested in a specific set of dictionaries, which is the set of dictionary where each dictionary element, each atom, has unit L2. Alright? So we can actually equivalently rewrite this formulation as the optimization over a function of D only. And I denote this function by f of n. And so basically f of n is obtained by minimizing out the decomposition A. And so basically f of n is defined as the average over function f of x that are the sparse coding function for a single signal. So in spite of the fact that sparse coding has led to good performance in many tasks, there have only been a few theoretical analyses that support this evidence. Basically, there are two lines of work. On the one hand, some people try to characterize the generalization property of sparse coding by deriving some non-asymptotic bounds, generalization bounds. And on the other hand, and this is going to be the topic of the talk today, there's a second type of analysis which is known as identifiability analysis. And so in this context, instead of focusing on the very difficult question of trying to characterize a family of global minima, we are interested in a slightly simpler question, which consists first in assuming a sparse model of the signals, where we have some fixed dictionary 0 here, fixed reference dictionary, and some sparse beta alpha 0. And the question that we ask is, does the function f of n has some local minima around this fixed dictionary? And so Valencinas has provided the first answer to this question in the case of noiseless signal and in the case where the dictionary is the basis. This first work has been extended to the case of other dictionary, but still in a noiseless setting. What we will try to do today in this talk is to go one step further and to try to extend this work in the case of noisy signals, also outliers in the signal models, and in the case of over complete dictionaries. And so to be a little bit more specific, we will consider some probabilistic model for the signals with some knobs. That is, x is going to be the signal x is going to be generated as the product d0 times alpha 0 for some sparse random vectors alpha 0 plus some random noise epsilon. And so the goal will be to try to characterize in a non-asymptotic way the probability with respect to the different sources of randomness in the problem of finding a local minima in a certain neighborhood that has to be characterized for the function f of n. And so for convenience, I just remind you this the definition of the function of f of n that's going to be central throughout my talk. Alright, so it's the average of the sparse timing function for a single signal. So there is an important remark to make at this stage of the analysis is that as soon as we consider this formulation, these objective functions, there are basically some invariants, which is sign flips of the dictionary and atom permutations that are intrinsic to this formulation, and this results in the fact that we cannot hope for exactly identifying the dictionary D0, but the best we can do is basically to consider the equivalence class of all the transformation of the dictionary D0 with respect to those operations, which is sign flips and atom permutations. If we want to do better than this, we have to change the formulation. So perhaps some motivation why should we care about this problem of identifiability. So first I consider that this problem where we consider a very simple scenario is basically a sanity check. We would like just to verify that sparse coding is doing what we expect it to do. The second motivation is to better understand the role of the parameters that are involved in sparse coding. So for instance, I mentioned here the number of atoms, which is a parameter which is in practice difficult to set and is not very well understood in the case of other complete regimes. It would also be interesting through the non-asymptotic analysis to better understand what is the level of noise and the fraction of outliers that can be acceptable in this context. And in the same way, and perhaps as a guideline for some practitioners, it would be interesting to understand the sample complexity of sparse coding in the sense that it will help to practice how many signals do I need to hope to learn a good dictionary, basically. There is a third motivation which is related to optimization this time. So as we will see, or implicitly see, in an analysis we actually see what are the contribution of the curvature, what parameter contribute to the curvature of the function f of n around some local minima, and by understanding this, this would perhaps pave the way for the design of new optimization strategies. So there are a couple of questions that are raised by our objectives, and so I'd like to present a few of them, and basically those questions represent the roadmap that I will follow in my talk. So interestingly, the questions are related to different aspects. The first aspects are related to geometrical and optimization ingredients. So the first question that I will be interested in is how can we characterize the local minima over the specific set of dictionary, especially with this function of f of n, which is somewhat intricate in the sense that it is defined through the minimization over the decomposition. It is not convex. We don't know exactly what is its degree of smoothness is, so this function is quite complicated. There are also some ingredients related to statistical aspects. So I mentioned probability. So what is going to be exactly the probability model I will consider for x? Will I need some assumption on the reference dictionary? And also I mentioned that the goal will be to obtain some non-asymptotic results. So what are going to be the tools that I will need in this context? So let me begin with the geometry of the set of dictionary and the characterization of local minima. So the starting point of our analysis is to try to exploit the geometry of the set of dictionary. So remember that the set of dictionary is basically a product of sphere. Each dictionary element is forced to have some unit L2 norm. So this set of dictionary is actually known as the manifold, it's known as the oblique manifold. And the idea will be to parameterize this set of dictionary through a family of curves that will all go through the reference dictionary V0. And so I introduced this family of curves, which is defined as T, and that depends on three parameters, W, V, and T. So let me explain you what does this parameter mean. So basically T is a non-negative scalar, and it can be seen as a radius, while the matrix W and the vector V can be seen as parameters that define the directions of the curve. And more specifically, the matrix W belongs to the tangent space at the reference dictionary D0. Right? So let me show you some illustration of this family of curves. So if we have the manifold here, and we draw one of these curves, so basically it goes to the point D0, and if you take the tangent at this point, you obtain this matrix here. So you can easily check that if you take here the radius equal to 0, the cos is equal to 1, and the sine disappears, and you basically get back the reference dictionary. And you can also easily check that for all set of parameters, the curve is indeed in the set of dictionary. Right? So now, based on this parameterization of the set of dictionary, we will be able to characterize some local minima. More specifically, if we consider some radius tau, and if we're able to show that the function f of n takes greater value than the function f of n at D0 for all curves parameterized by W and V for this radius tau. So if we're able to show this, then we can conclude that the function f of n admits some local minima in this ball here, which is centered at the reference dictionary. So just to give you the intuition of a very simplified case in 1D. So basically, if you manage to find an interval here that contains D0, and at the border of at the edges of this interval, you can show that the function takes greater value than the function at D0. Basically, thanks to compactness and continuity argument, you can conclude that there is indeed a local minimum inside the interval also. This is a very simplified view of what's going on because there's no geometry of the manifold involved here, but just to get an intuition of what happens. So, as we can see now, the problem of finding the local minima can be reduced to showing this inequality, and which means that we will have to be able to fully exploit the expression of n, and we have to closely work with this function. So now the second part of the analysis is concerned with the simplification of this function f of n, which we have seen was somewhat complicated. So the main idea behind trying to simplify the function f of n is to use some ideas related to support recovery. So what do I mean by this? Let's have a look at the function f of n for a single signal. So if we assume that this function here has some solution has hat with corresponding support j, if we also assume that this matrix here, dj transpose dj, is invertible, and if we also control the sign vectors of this solution here, we will define it by S. So it's quite easy to show that the function f of x coincides with another function, a surrogate function, for which we have an explicit form. So beyond the exact expression of this surrogate function, what is important to keep in mind is that as soon as we're able to control the sign of this solution here, we can have simple expression for the function. So this is the main message. So when are we going to be able to exploit this fact? So we have just seen that under some mild coefficient, we can show that the function f of x of interest coincides with the surrogate function. So now, in the perspective of having to make some probabilistic control afterwards, it's important to notice that this sign vector here is actually random variables that depend on all sources of randomness, alpha 0 and the noise. So a natural question that arises is when can we simplify this, the sign of this solution by asking to be equal to the sign of the true generating coefficients, which would mean that we would get rid of the dependency with respect to the noise here. And so this question actually exactly corresponds to exact support recovery, which has been the topic of regular research for L1 regularized discourse problems. But here we have to, although we are interested in exact support recovery, it's important to notice that the setting is slightly different here. Because although the signals are generated according to the models, we are not interested in support recovery only at this dictionary here, but we also would like to obtain support recovery for a dictionary along the curve, which is a little bit, which is next to D0, which is different from D0, but not too far away. And what this means is that we will have to extend exact support recovery to take into account this dictionary perturbation. And so if we introduce this event, the event E coincide, where the function of interest coincides with the surrogate function, this time indexed by the sign of the true generating coefficient, it turns that we can show that this event here happens with high probability, provided that the perturbation T is small enough. To the initial goal we had. So just remember that to prove that there exists a local minima, it's sufficient to prove this inequality for all direction. And so, since it is complicated to work directly on the function f of n, what we will do is to construct a lower bound on this difference and show that the lower bound is itself strictly positive. And the idea behind that is we can actually always control the difference of the function f of x and the surrogate that we have introduced before. The idea is that based on the definition of these two functions, it's quite easy to show that they are both bounded by the energy of the signals. And so if you basically apply the triangle inequality, it's not complicated to see that the difference of those two functions is represented this way. That is, either the function coincide, as we have seen it before, in which case the difference is equal to 0, or if they do not coincide, we have a symbol of a bound by the energy of the signal. And so if we sum over each signal, set of n signals in order to get back to the function f of n, we obtain this conclusion, which is we have the difference of the function f of n, which is bounded by our surrogate function phi of n minus some residual term r of n that basically measure how often the surrogate and the function disagree. Alright? And so now the objective is to prove that this lower bound here will be strictly positive. So let's discuss quickly the probabilistic aspect of the problem. So we mentioned that we will consider a probabilistic model for the signal, so let me detail a little bit the aspect of this generative model. So the signal is generated in this way. As I mentioned before, the reference dictionary is going to be fixed here, and we will assume we'll make some assumption on the dictionary D0, and those assumptions will rely on the coherence of this dictionary. So just the coherence is basically a measure of the level of correlation inside the dictionary. The sparse random vectors alpha 0 are going to be generated in the following way. So we first draw a support of a fixed size, which of size k. Then for the coefficient that are outside of the support we have just drawn, we've set the coefficient equal to 0. And for the coefficient inside the supports, we assume that those coefficients are generated according to some bounded symmetric distribution. And the bounds of this distribution are given here. And finally, the noise is assumed Gaussian with some variance sigma squared. Alright. So let's get back to our objective. We have seen that we wanted to prove that this flow down here is strictly positive for all directions indexed by W and V. In fact, with some careful computation, we can pretty simply handle the concentration and the probabilistic control of the blue term here and the orange term here, based on some standard techniques. And the uniformity with respect to the directions is handled by some epsilon net techniques. So it's just detail, it's not, I go quickly over this slide, even though this is the part in practice that takes most of the time. But so let's discuss now the result we obtain. So here, for simplicity, I will consider that the bounds of the distribution of the coefficient alpha 0, the ratio of those bounds are constants. We have an explicit dependence with respect to those parameters, but I just consider here for simplicity that those are constants. Right. So we need to introduce this parameter theta that depends on, I remind you, the sparsity level k, the full size of the dictionary P, and the size of the signal dimension L. And so based on this parameter theta, we can make a set of assumptions that will drive the scaling of the problem. So if we consider the radius tau, which of this order of magnitude, if we assume that we have enough signals to verify this inequality here, if the dictionary is incoherent enough according to this scaling here, and if the noise level is small enough according to this inequality, then we can conclude that with high probability we indeed have a local minima in the law we have introduced before, centered at the dictionary D0. So just to give you the main idea, the main trend that is highlighted by these results. So the idea is that the more localized we want the local minima, that is the smaller the radius, the more points, the more observation we need, and the smaller the noise has to be. So this is quite a natural conclusion we obtain. So I have put here in blue this coefficient 5 that might look a little bit weird, but I'm pretty sure it's not. It's far from being optimal, and I'm pretty sure it could be reduced. Another scaling that we would like to improve is this coherence assumption, which is quite strong at the moment, and we will hope to get rid of the dependence with respect to the full size of the dictionary here. So let me now conclude and give some take-home message regarding this analysis. So we have shown that it was possible to prove that sparse coding admits some local minima in this specific generative model of sparse signals. And as opposed to previous work, we were able to consider the case of noisy signals. I actually have not had time to mention that and to explain how we can consider outliers in this setting, but we can actually extend our generative model to include some fraction of outliers and still be able to guarantee the existence of a local minimum. The idea is that our analysis actually only relies on the energy of the bad signals in one sense. So we can basically consider everything as soon as we control the energy of all those bad signals. I have tried to lay the emphasis on the analysis, and I just had one slide of the result because I tend to believe that the analysis itself is interesting, and tend to highlight some interesting aspects, notably the fact that it relies on different considerations of different nature, geometry, optimization, and statistics. And as future directions, it would be interesting to consider more general and more realistic signal models, for instance, based on compressible priors or spike and slab priors. And finally, it would also be interesting to understand what is the role of more structured, more complicated regularization, which is a topic which is not well understood yet in the context of matrix characterization. Okay, this is it, and thank you for your attention.
We have time for a couple of questions.
So, yeah, I was wondering, so the hypothesis you use is based on coherence, which in practical dictionary is usually very bad. And I'm wondering whether you could put a signal model that could actually depend on the dictionary D0 and use a method based more on the support itself, like exact recovery condition of crop, for instance. This would be very useful for image processing dictionaries that have very bad coherence, but where you could actually have some result using ERC if you constrain your spikes not to be too close, for instance.
Yeah. So yeah, it's true that in fact in the end we have to prove our we need this assumption to guarantee exact support recovery, but we assume them through the coherence, so which is way stronger. It's true. Perhaps there is some room for improvement and, in this respect, and it would be possible to consider this kind of assumption, although it's not as convenient to manipulate expression based on this ERC. Another way that we at some point considered is to not consider deterministic coherence-based assumption, but probabilistic-based assumption, which would reduce the scaling not in 1 over k, but 1 over log p. This is also work related proposed by Trop, and so perhaps this might be a way to reduce the stringent assumption on the coherence.
Other questions?
I'd like to understand whether you need that the ratio of the smallest and largest coefficients has to be bounded by a constant.
No, okay. It was really just for simplicity. If you want, if you prefer, instead of saying this, I could have made this expression here more complicated with an explicit dependence with respect to those parallels. Okay, it was for simplicity to just give the simplest big O notation I could. And if you want some detail, we can also explicit what is behind those big O.
Do you see any difficulties in extending that to a complex case?
The complex case? You mean extending this analysis to the case of complex signals? To be honest, I have not worked much with complex, so I don't see where would be the bottleneck. But
because you can have a rotation on the
machine, I think it makes a difference.
It makes a difference?
Yeah, if you change the manifold, but it would be.
No, but to control, because here you use the sign that you control, and then the sign becomes a complex number of modulus 1, so it's a little bit more tricky to. For instance, the lemma you put at the beginning, the stability of the support. It's still true, but
it depends on the complex. If the dictionary is complex and the signal is complex, this is easy. So you mean complex? What is complex? The signals?
The signals and the pitch.
The alphas are not complex.
Oh, exactly. Okay.
You want the alpha to be complex?
Yeah, we can. Yeah. Well, I mean, you can put the face in the dictionary, but yeah, no, both being complex.
Okay.
It's L1, L2 now.
Yeah, that would be. This is tough. But you can formulate it as a group sparsity problem. Yeah, but you need 2 subnets, one for the alpha, one for the.
It's probably doable, but.
Thank you.
All right, we should probably so let's thank the speaker.